this is Dr. Mad. Again, again, and again. But this final one. Okay, I promise. Well, sort of. Anyway, oh, moment of truth. Bell's experiment. Actually, Bell's experiment was based on another, a thought experiment by, guess who? Albert Einstein, of course. Yeah, with two other guys, Podolsky and Rosen, he thought about this experiment, to prove again that quantum physics was just a crazy theory. And so Bell got inspired by that, but he changed a few things. And also in particular, he originally thought of using electrons and their spin characteristics. But eventually, the real experiment was made by a French guy, well, French team guys. Yeah, oui, baby, oui, baby. Yeah, Alan Aspect. It actually was his PhD thesis. And as a matter of fact, John Bell was member of the jury for this thesis, which occurred 17 years after Bell's inequation, So, but anyway, who cares? Now it's time to have a look at the results of this experiment. Wow. Okay, let's summarize what we've seen first, to make sure we understand what we're really looking at here. Well, Bell said and proved, and we have proved together with him, that there is a way to design an experiment where we can show that quantum physics is not complete. There's something missing there, which was, again, Einstein's idea originally. And so we're going to make an experiment, and when we look at the results, we're going to calculate some value here based on the results, and if this value, the absolute value, is smaller than or equal to 2, then in all cases, then, we somewhat prove that quantum physics is wrong. And of course, if it's greater than 2, then, well, we proved that Einstein's was wrong. Okay, so again, the experiment that was made by Aspect and his team was, generate a couple of entangled photons and then see what happens here, and look at the results, look at the correlations between the results, and then drive to a conclusion. Okay? So, the winner is, well, let's look at Alan Aspect's experiment results. So this is the curve that was, the theoretical curve in black here, showing what the results should look like if quantum theory is correct, of course, because here we're going above the +2 and minus, and below the -2 line. And the results are shown in red here. Yeah, I know. Yes, the results were actually showing that quantum theory is right. I know. So let's draw some conclusions from that. Again, we have to remember that, the problem that we get here is that the photon going to this filter here and decides, which polarization it's going to take, what we call polarization so far. And then it will somehow transfer that information to the other photon, the entangled one, here, so that it has some influence there. So that means by just, for instance, changing the angle of this filter, well, you'll get different results here, So let's keep some kind of causality, between here and there. There's one kind of problem, that's something pretty weird. But what's even weirder, and which is also derived by quantum theory, is that this information is actually instantaneously passed to this photon, you know. So at the same time that this photon decides to go one way, this photon will use the same polarization. And this has been, you know, proven. There has been so many experiments done between that time, you know. Aspect experiment was in 1982. And there's one in 2013 made by a Chinese team, you know, led by Professor Hyun Yin. Sorry for my Chinese accent, you know, it's even worse than my English accent, so it's pretty bad. So anyway, they made an experiment, you know, similar to this one, with the filters here set apart, you know, like 15 kilometers apart, you know, something like almost 10 miles, you know, away from each other. And then there were some synchronized clocks, and there were, I mean, it's an amazing experiment actually. If you know look it up in internet, it's incredible. But anyway, the result was that the information there had been transferred at 10,000 times the speed of light. At least at 10,000 times the speed of light. That's, you know, the practical result. The theoretical result was an infinite time faster than speed of light, because it was supposed to be instantaneous. But in any case, you know, not only we have a causality, but we have the so-called non-local causality, which also was a big problem for Albert Einstein, you know. But this time it's been proven, you know, by an experiment. So that's even crazier, you know. Anyway, so what have we learned? Well, first of all, you know, Einstein was wrong. And that's a big deal, you know, because Einstein was kind of a genius, yeah. And, you know, the guys who followed his lead and you know, had the same agreement, you know, had the same ideas as Einstein, were pretty good guys too, you know, pretty clever, pretty smart guys, you know, like Schrödinger and others. And all these guys were wrong regarding quantum physics. So that was a big deal. A second thing, which is, you know, more, let's say, physical, is that, well, you can forget about local causality. And that's a problem, you know, because that means it's something that we don't really understand, to be honest, right? About things, how things go today in our physical world. And well, of course, if you accept quantum physics, there are other things, you know, that you have to accept, like, you know, some things happen for no particular reason, you know, there's just random, you know. No, I'm going to pick this one. No, I'm going to pick this one. But why? Not because. There's no reason, you know. Well, of course, there are realistic camp. Remember the first video? Well, said, no, you know, if you have enough information, you should derive that from somewhere, you know, and then it will explain why you make a choice or another one. But for quantum physics, you know, Heisenberg and Bohr and all this guy, no, you know, it's just random. So, anyway, that concludes our, you know, series of videos. And I hope we fulfill the purpose, which was, remember that what we wanted to do was to prove by ourselves that quantum physics was crazy. Yeah, it is crazy, right? And we also proved that, well, but it works. So, at least I hope that now you better understand when you read some, you know, some documentation on publications on internet or wherever, and you probably be able to say, oh, this guy understood it, or this guy, no, does not understand it, which is, you know, sometimes pretty scary actually, what you get on internet. But anyway, okay, so what's the next step? Well, you know, for now, we can imagine many different things, but then we go to the subjective, you know, path. And you know, I don't want to include that in these videos, because these videos I think, are pretty objective, from a scientific standpoint. And so I think while we can trust, what we've seen here, without even using, quantum theory thing. I've used, in all these videos, I've used actually pretty old theories, both from physics and from mathematics. I didn't use latest bells and whistles that we get in physics, like the quantum field or supersymmetry or, whatever thing. And in mathematics, same thing, there are many ways to explain, the Bell's experiment. But I wanted to keep it as simple as possible and yet still have, a logical and rational way of, thinking through things. So I hope I managed to do that, and we managed to do that together. But then, we can probably ask ourselves some questions about, science and science models and things like that. But again, then we go to the more subjective matter. And so maybe I'll make a different video about that. But, in any case, I hope you enjoy that. Keep an open mind, and you'll be a big, great scientist. Bye.